Yes, this time we'll be talking about text classification. This is important for a couple of reasons. Number one, it's one of the most, fundamental natural language processing tasks. Number two, this is what you'll be doing in your first assignment, so you should know the basics. Number three, I'm going to talk about a few auxiliary things that aren't specific to text classification, but very important across NLP or experimentation in general. So those are also good things to know, and parts of them will also be part of your assignments as well. Another reason why you should be listening today is we're having quizzes starting today, so you should pay attention to make sure you can answer the questions on the quizzes. Again, the quizzes aren't really meant to trick you or punish you or anything. They should be easy as long as you're paying attention. So, our goal is that they will be easy as long as you're paying attention. So, yeah.
Reminder about the rate
limit. And the weight. So one other thing is we have a wait list for the class, but we have cleared everybody off the wait list if you don't have a conflict. So if anybody is still on the wait list and watching on Zoom or something like that, then that means you have a conflict. So you need to remove the conflict and then we can move you into the class. Cool. One other thing is on Piazza, I saw a couple questions that we haven't been able to answer yet. So maybe I can just answer them now, and one of the TAs can add them to Piazza. But there were questions about how to solve assignment 1, or how should I know what I need to do to solve assignment 1. I very much admire your being well ahead of things, but actually we haven't covered the content on assignment 1 yet. So one option is wait until we cover the content, and that will be in 3 or 4 more classes, I guess. So that would be my preferred option. Otherwise, you can read about what BERT is and what transformers are and stuff like that, and then you might have a pretty good idea. So I think we'll also have a walkthrough for assignment 1 at some point, probably maybe right after those classes. Are there any other questions before we get started? How long after classes do we have to take the quiz? It'll usually be 24 hours after the class or 24 hours after we release the quiz. So it'll be by the next day, so you can get it done before the next class. Anything else? Okay, great. So text classification, this is a slide that I showed yesterday. It's a general framework for natural language processing, describing natural language processing tasks. And this time we're specifically going to be talking about text classification, which we talked about last time. However, the difference between what we talked about last time is now, instead of doing a rule-based method, which we did last time, we're going to be doing a machine learning based method from paired data. Sorry, before I get started, I see a question. I just got off the wait list and don't have access to Canvas. We'll figure that out. If you could send an email to the TA mailing list or stuff. And actually, thank you, TA, for taking a look at that. Okay, so now going back to the main class content, as a reminder, this is our setup for machine learning. We have a large training data set. We put it into some variety of learning algorithm, and we have a learned feature extractor and scoring function, which we can then use to basically optimize our loss function, or attempting to optimize our accuracy at solving the task that we want to solve. And then we have an inference algorithm that allows us to decide which output we're going to be generating. So for text classification, normally what we're doing is we're classifying sentences according to individual traits. And those traits can be a bunch of different things. They can be topic, they can be sentiment, they can be subjectivity, objectivity, they can be whether the sentence. Oh, another good example is the intent classification that we talked about failing for Google queries before, where I said, who invented neural machine translation, and it tried to translate the sentence for me. So all of these are text classification tasks. Put in a text, output a label, discrete label. And this is the example that we talked about last time. So now, moving beyond that, I'm going to be talking about generative and discriminative models for text classification. So these are two very, very broad varieties of models that we can use for a bunch of different tasks. And basically what they boil down to is the way they do classification, or actually the way they do modeling in general. So a generative model, basically what it does is it calculates the probability of some data. And so if X is our data or our input data, we calculate the likelihood that that X would appear in the new data set that we found that was from the same training distribution that we saw before. So I assume that at least one person in this class will be able to answer this without me giving the answer, but what's maybe the most famous generative model for NLP? Oh, I've heard a lot of different things. What were the answers? GPT-3. Okay. Yeah, I was thinking a little bit more broad than that, but sure, GPT-3. I meant language models in general. So, but yeah, GPT-3 is a good example of a language model. There's also models that try to model a joint probability, and the joint probability is where we have different variables, and we want to model the probability that both of them occur together. And very often when we talk about a joint probability like X and Y are different varieties of data. And then on the other hand, a discriminative model is where we have a model that calculates the probability of some sort of trait given the input data that we receive. So it's this conditional probability here. So both of these are very, very useful. And both of these can also be used for text classification. So in the text of text classification, the more common variety of text classifier is a discriminative model below, where we take in a text X and output Y. But we can also model the joint probability of X and Y and use a generative model here as well. And I'll show you how we do each of these. So basically, that's what I said before. We learn a joint model of X and the label Y. And then over all of the possible Ys, we take the maximum one and return it as our answer. And then for discriminative text classification, we calculate the probability of Y given X and return our answer. So it's very similar other than how we calculate the probability here. It's very similar other than how we calculate the probability here, but actually under the hood, there are a number of things that will have to change. So I'm going to take the unusual route and talk about generative text classification first. And in order to do generative text classification, the first thing we'd like to talk about is language modeling. And language modeling is basically calculating the probability of a text. And if we're just talking about calculating the probability of a text X, the most common way to do this is by taking the product of the probabilities of each word or token in the text conditioned on all of the previous probabilities. So this is the next word, and this is the context. We don't necessarily have to do it this way. There's no reason why we couldn't calculate the probability of the previous word given all the, all the words after that, or just randomly shuffle the order of the words and calculate the probability of the words in that randomly shuffled order. But humans read from left to right. Not always, of course, if you speak like Arabic or Hebrew or something like this, but at the very least, humans listen from the past to the future, right? So there's a natural ordering of language, and we might as well model language in that way. And so then the big problem here becomes, how do we predict the probability of the next word? And any questions or discussion so far? Yes.
But it's not always certain that the previous word would be able to determine the next word. I mean, so if we have a sentence like that, have to go to the bank. So it could be a river bank, or it could be the financial bank. And depending on the next word's context, we can maybe decipher that better. And I want to do this.
Yeah, that's true. So it's definitely the case that we cannot predict the next word with 100% certainty. Just to give a kind of trivial example, at the beginning of a sentence, you're almost certain to not be able to predict the first word. I mean, sure, the word "the" is most likely to be, it's the most likely thing you'll see at the beginning of a sentence, but still, that's not even 50% of the probabilities. So that being said, what we're trying to do is we're trying to model the probability distribution of all language. So we don't have to have certainty. We just need to accurately predict the probability that the next word is going to occur. Yeah.
I think it's also good to address the point that we're modeling surface tokens here, not word sensitive.
Yeah, that's true. So, and the bank example is a very typical example of word sense, like ambiguity, but that's not what we're handling.
We're only worried about the letters, not the.
Yeah. Yes.
When we talk about the probability of sentence, are we talking about the sentence in the context of the corpus, or?
Right. And so actually on my slide, I said sentence, but out loud, I said text. And actually text is probably more accurate because we might be modeling a sentence, we might be modeling a document, we might be modeling a book, or we might be modeling a search query, which is just like a few words or something like that. So it could be any length of text. So thank you for the reminder that I should be repeating the question from the live audience, so the people on Zoom can hear. And the question from the live audience was, what about why do I write sentence on this slide here? And the answer is, it doesn't necessarily need to be a sentence. Another question from the live audience that I just had before this was like, isn't there some ambiguity? So wouldn't you be able to not model like the next word without, with absolute certainty? And yes, the answer to that is yes. Okay, cool. So I will move to the next one. So modeling the probability of the next token is a really hard problem. And in fact, we talk about people training large language models like GPT-3 or PaLM. They spend millions and millions of dollars and hundreds of thousands or millions of GPU hours on doing this to solve this problem. So you're not going to get the answer right away in your first class or in your second class of natural language processing. So I'm going to give you the very simple way you can do it without spending $1 million and very, very efficiently. And the way you can do it is with a count-based model. And what count-based models do is they basically, they count things up and count up frequencies and divide in order to calculate the probability of, a certain phenomenon happening. And in this case, we're talking about the probability of a word. And to make things even simpler, we're going to make a very, very rough independence assumption, which is to say that the probability of the next word is equal to the probability, is independent of the previous words. And then once we do this, there's a very, very simple way of calculating the probability of the next word, which is just, we count the number of times a particular word happens, and we divide by the total number of words in our corpus. And so if we do this, then, the word "the" is the most common word in the English language. And so it would have a probability of, I don't know what, 0.15 or something like this. That would be the highest one. Then you get with 0.1 and so on. You go down the probability from there. And then once we have this probability, this is called the maximum likelihood probability because this way of counting up and dividing will maximize the likelihood of the training corpus. So this is a maximum likelihood estimator for a count-based model. And then we just apply this to calculate our probabilities. So then we would take this maximum likelihood probability and multiply the maximum likelihood probabilities together to get the probability over the whole text that we want to calculate. So overall, this is pretty simple. I imagine that most people in the class could go and implement this in Python and you'd have your first language model. Are there any questions about details or? So, okay. However, there are some tricky parts here. The first tricky part is handling unknown words. So it's not necessarily the case that every word will exist in your training data. And in fact, for any non-trivial corpus, you're almost guaranteed that not every word is going to appear in your training data because, you know, we invent new words all the time. There might be a misspelling of actual word or noise or anything like that. So if the word doesn't exist in the training data, then this probability here will become 0. And then if you're taking the product of all of these probabilities, then multiplying anything by 0 becomes 0. So you'll get a probability of 0, which is not very interesting, right? And so because of this, we need a distribution that assigns some probability to all words. I kind of flashed that on the screen and gave away one of the answers, but does anybody have any ideas about how we could do this? Add a bias. What would the bias look like? Laplacian smoothing. So what could you explain briefly what Laplacian smoothing?
Add a small function with all counts. That nothing is 0.
Okay, so the answer is add Laplacian smoothing, which adds a constant to all counts, so that the numerator never becomes 0. So just to show what that looks like, and I hope that people on Zoom can also see this, we would say C train of X plus 1. So we would get something like this. So this is a good idea, but it won't work. Why won't it work? Any ideas?
Words outside of the training.
Exactly. So words outside of the training corpus would have 0 probability, or maybe a slightly more accurate way to say this is we need to have some set of all words. Let's call it W. Or actually, let's call it V for our vocabulary. And there's no like reasonable way to assign this other than making it infinite, like, you know, all combinations of characters. And when it becomes infinite, then it washes out all of your probability and you get nearly 0 probability. So what's another idea? Yeah.
Break up it into subwords which might have been seen before.
Break it up into subwords, which it might have seen before. So yes, that's a good answer. And that's essentially what a lot of modern NLP models do. Before I go into like the details of what a subword is, we're going to cover this in more detail later. You could just think of like every character, right? Model every character one at a time. And if you do this, then if you do this and you model each character one at a time, you might be able to say, well, the number of characters in the world is limited. We can just say our character vocabulary V is fixed. And what would be a good estimate for the number of characters in the world? Any ideas? How would we do that? Using ASCII or Unicode. Yes, that's a good answer. Using ASCII would be pretty boring because then you could only do English. So I would prefer Unicode. And you know, I don't know the exact number of Unicode characters. I think it's something on the order of like 30,000 or something like this. 20 to 30,000, maybe a bit more than that. So then, you know, at least you would have an idea of like what your denominator there could be. For subwords, I'll just give you, yeah, sorry, go ahead. can we also blank out words at random and count the probability of a blank occurring in our corpus was the question. A very, very good point. And that's actually the next thing that I had here. Oh no. Okay. Yeah, so sorry. I made things a little bit more complicated than they should be on this slide. I do have a question in Zoom, and the question in Zoom was the denominator in the formula I wrote should be the size of v instead of 1. And sorry, this is a little bit ambiguous, but what I meant by this formula was this. Like there should be parentheses here, in which case the formula is correct. So yeah, so basically there's kind of two ways you can handle this. One way you can handle this is you can make it so that your vocabulary is sufficient to cover every string that you'll want to be generating. One way to do this is like, let's say the word is I have, or the thing that you want to model is I have decided. So you can break it up into characters and model each character at a time. Another way you can do it is you can break up into words and model each word at a time, but that has the unknown word problem. And another way you can do this is you can break it up into subwords, which are sufficient, which are like longer than characters, but shorter than words. And then you can kind of stick together the subwords. And this is a very common thing to do now. It's in like BERT, it's in GPT, it's in all of the models that you'll be using downstream. And I think Bob is going to talk about this later, like sentence piece and other methods for doing this. But the most important thing you have to know is that right now is that there's a black box program that can, in an unsupervised way, discover these subwords and split them up for you. And then if you can do that, you can split things up into subwords, and then you can concatenate them back together. So it's kind of like a mix between the characters and the words. Okay, great. And we can ignore the uniform distribution thing there. So yeah. Actually, so like this is one way that you could do it. I'll just to explain what you could do. You could also do the thing that was mentioned before, like whenever you have a word in your training corpus, for example, a word that only appeared once, you could say, I'm not going to model this as an actual word, but I'm going to treat this as unc. I'm going to treat it as an unknown word. And then instead of predicting here the actual word decided, you would predict unc. And then after you've predicted unc, you switch over to another model that predicts the probability of the spelling of an unknown word. And that could be based on characters or something like this. So this is another way you could do things. And that's what I've written on the slide. But actually, the most common way of doing things is by like splitting things up into subwords and then modeling the subwords. Yeah.
Could you use a validation set to predict the probability of unknown tokens?
Could you use a validation set to predict the probability of unknown tokens? Yes. Basically, you can do that. The most common way of doing things is instead of using it to predict the probability of an unknown token, what you do is you use it to like predict the probability of this smoothing here. There's a lot of different like smoothing methods. Like this is called like Dirichlet smoothing or additive smoothing, and then there's a lot of other methods too, which like actually. Instead of adding something, it's actually better to subtract something, subtract a value, and then add all of the extra probability to unknown words. I'm not going to go a lot into the mathematical details, but the basic reason why is because almost all of language has this long tail distribution where very frequent words are very frequent and very infrequent words are very infrequent. And this like subtraction is a better model of that distribution. But if this was a in NLP class 10 years ago, I would have taught a whole lot about that, but like, honestly, we don't use account-based models that much anymore. So I've kind of skimmed over.
I think you misspoke. There are a few very frequent words and many very infrequent words.
A few very frequent words and many very infrequent words.
And there's some questions in the chat that you might want to.
Okay. So do we treat the white spaces the same as other characters in character-based models as if they are functional characters as well? It seems that white spaces are not emphasized as much in word and subword-based models. So this is a very good question. In character-based, in any model, you need to be able to model the fact that a white space exists. And the reason why is because otherwise you would have no way of knowing like the difference between I have like the best example in Japanese, but I don't have the best example in
Japanese. We'll see if we know.
No, I'm not going to say it in Japanese, but like you could come up with somebody could probably find an example online of a thing where the spacing is ambiguous in English, but you know, like I am a dog or something, and I mad dog, which I don't know. I kind of want to imagine what I am mad dog, like what kind of person would be saying that, but you know, basically, like spacing is very important in English to determine, you know, the different what the different words are. And so if you don't model spaces in some way in your model, you're going to have trouble. And so in a character-based model, you have to model spaces like any other character because you need to insert them at the correct places. In a subword-based model, actually the most common way to do it is you have different characters, or you have different tokens like this. And before each token that has a space before it, you add like kind of a special space character that indicates that you should be inserting a space there. And any token that doesn't have the space character before it, you don't have that token like assigned, like you don't have that special character at the beginning of the token. So now, you know, like there's a very simple way to reproduce the original sentence, which is all the spaces and then turn all of these like special characters into spaces.
They put on that Domo line.
So yeah, everyone, if you're listening on Zoom, please mute yourself. And then the second question is, what is the difference between a subword and a stem? So that's another good question as well. I would say a stem is a subword, but not all subwords are stems. So a stem is basically a piece of a word. And usually it's the first piece of a word after you've removed some sort of like linguistically meaningful suffix. And a subword could just be any piece of a word. So even this D here is a subword. Okay, great. Cool. So up until this point, we have been talking about a product of probabilities. Another important thing that we need to know for just about any model we're training is that we tend to express our models in log space. So instead of the product of probabilities, we take the sum of log probabilities. And essentially the product, you know, if you know your logs, which I'm assuming that most people here do, you know that if you just take the log of the left side, the log of the right side, then this will be mathematically correct. And the reason why we do this is for a couple of reasons. The most important reason is numerical stability. And, you know, on modern computational hardware, if we multiply together a whole bunch of small numbers like probabilities, eventually we're going to underflow and it's going to turn into zero. And that's the main reason. But there's also some other convenient things as well. So for the purpose of comparing these models to other models that we're going to be talking about in a second, I'd like to mention that we can parameterize a count-based unigram model by expressing parameters as the log probability of each word as a parameter theta for that particular word. And so we can parameterize our model like this. And given this, we can take a generative text classifier. And the generative text classifier, we have our joint probability. And our joint probability can be based on the following decomposition. So if we know the chain rule of probability, we can basically say the joint is equal to the probability of one of the two variables and the conditional probability of the other variable given this variable here. And so what this is this is a class conditional language model. And the class conditional language model, for example, could be trained on data associated with that class, associated with the first class. And then we can also have a class prior probability, which we can also view kind of as the bias, like the bias that we had in the text classifier last time. And so this is essentially what the probability here looks like. And so up until now, I was talking about a language model, and suddenly I switched to like a class conditional language model. So a language model conditioned on each particular class. But the easiest and simplest way to do this is just train on the data from that class. So we have a bunch of positive reviews, we have a bunch of negative reviews. We train only on the positive reviews, we train only on the negative reviews, and we have two language models. Any questions here? No? Okay. So if we look at what our bag of words generative classifier might look like, what we can do essentially is we have a big parameter vector where the parameter vector is the class conditional probability of each of the words in the vocabulary. And we have a log probability here, which is essentially our bias term, and our bias term is always active, like we talked about last week. And then we add up the frequency of all of the words in the input sentence, we multiply it by this vector here, and we calculate a score for each class. And then whichever class gets the highest score is the one that we will be outputting. And this classifier is also often called a naive Bayes classifier. More generally, not necessarily only for language modeling, but that's another widely used thing. So is this basically clear? Sorry to surprise and wake up everybody with my sparkling water. Okay, great. So one other thing I should point out to make sure that you guys don't think this is too boring is there's no reason why this needs to be a Unigram language model. It could be GPT-3, right? It could be any language model we want, as long as we have some way of conditioning our language model on the class that we're trying to classify. So this isn't obsolete technology. This is something that you totally could use in the current setting that we have. So you can also keep that in mind. Okay, great. I'll move on to discriminative text classification. So generative text classifiers are relatively easy to understand. You could easily build one yourself by just counting and dividing. But actually, discriminative classifiers are used a bit more frequently. And why so? One of the reasons why is because generative classifiers are a somewhat roundabout way of modeling data. And they need to spend a lot of capacity on modeling the input. So for example, if we had, for example, a neural language model or something like this that was training, you would have to train perhaps a very long time to do topic classification because you would need to be training a language model that models all of the topical, text and trying to model the probability of the topical text well, when in reality, actually probably just looking up a few keywords is enough to tell you which topic something belongs to. So it would require a much stronger model than is necessary to do the task that you're trying to do in some cases. And so discriminative models directly model the probability of the output, which is what we care about. However, unlike Unigram models that I talked about before, discriminative models don't have an easy count-based decomposition. So we talked about our bag of words generative model, which we could easily calculate from count-based probabilities. But a discriminative model, there's no easy way to do something like this. So what do we do instead? So for discriminative model training, basically what we do is we define a model that calculates the probability directly based on the parameters theta. And so we have this probability of y given x conditioned on the parameters. And then we define a loss function that is lower if the model is better, such as the negative log likelihood of the output label given the training data. Which looks a bit wait, is that a mistake? Yeah, sorry, I'm thinking that that is a mistake in the equation. That should be the conditional probability. So that should be P of y given x. Like that. So then we optimize these parameters directly to minimize the loss. Like this. Okay, so because we talked about a bag of words based generative model, next we'll be talking about a bag of words based discriminative model. And we'll take the easy case of binary classification of positive and negative first. So what we do essentially is we first calculate a score. So this is the score of the label given the input. And the way we calculate it is by having our bias parameter and then the parameter of each of the output label given all of the input words in the input. And then we convert it into a probability. The most common way to convert this into a probability is using the sigmoid function. And the sigmoid function looks a little bit like this, or if you graph it on a graph, this is what it looks like. So if your value is 0, then you'll have a 50% probability of it being correct, of either label being correct. And the more positive it gets, the more likely the positive label is correct, and the more negative it gets, the more likely the negative label is correct. Yes.
Is the theta y given x basically a sum of
The theta y given xi. This is a single weight, actually. It's a weight for a single word in the sentence, input sentence. Yeah. And we can also expand this to multi-class classification, which is done using a softmax function. The sigmoid can be used for making binary decisions about whether something is true or not. For multi-class decisions, you calculate the score for each class and use the softmax, which basically takes the score, exponentiates the score, and then divides by the exponentiated score for all of the classes. And it looks a little bit like this. The good thing about the softmax is it's guaranteed to generate a well-formed probability distribution where all of the values are positive and they sum to 1. So one thing I should mention is maximum likelihood estimation using if we set this parameter here equal to the probability of the word given the class, then essentially this is the same as a generative model. So you can see that a generative model is just like a different way of predicting the same parameters as can be learned by this discriminative model. Yes.
Yeah, so I have a question about the both the sigmoid that the couple types doing this. So you know, when we say that we take a sigmoid and the output is 0 and 1, so we treat it as the probability
Mhm.
of the thing that we're trying to classify it on. And also there's, you know, the softmax, you know, we just think that the softmax gives us the probability of it being in that class. So I think that it does look like a probability distribution, right? It's between 0 and 1 and they add up to 1, right? So it looks like probability, but is there any inherent reason why we think that these arbitrary calculations will give us a probability, or other than the reason that it just looks like a probability output?
Okay, so this is a really good question. To repeat the question, it's basically this is the softmax is doing a transformation that turns the inputs into something that are between 0 and 1 and add up to 1. So that's the minimal condition that this is a probability distribution, right? But are we really sure that this is a probability, or is it just, you know, some function that's calculating something that looks like a probability, but it's not actually, you know, inherently probabilistically meaningful in any way? I'll get to you in a second. And then this is a really good question. One thing I should point out is that actually the softmax is used in some places where it's kind of decidedly not a probability. One good example of this would be attention, which we're going to be talking about in a little bit. There's nothing that has to do with, like, what attention does is it basically decides which information in the input to focus on. We'll talk about it in a few classes, but there's absolutely nothing that says like attention should be probabilistic in any way, or like it makes any sense to call it a probability. However, here there is one little thing that that makes it seem reasonably probabilistic, which is that we're trying to maximize the probability of getting the correct output. And because of that, if you have a very large amount of data, that you're training on, like let's say you have an infinite amount of data that you're training on, the optimal solution for that optimization problem of like maximizing the likelihood here will be a function that actually matches the probability distribution of the output text. So basically, like, the way we're optimizing the model encourages it to be a probability, a proper probability. However, there's a concept of calibration, which I believe I'm also going to talk about in more detail in a later class. But calibration is basically how good is your probability distribution? Like how, like, to give a very rough example, like if your classifier says it's 80% confident that the answer is positive, is it right 80% of the time? Is like what calibration says. There's actually a better mathematical definition, but that's kind of the idea. And there's a lot of work that shows that a lot of the neural networks that we train are not particularly well calibrated. So they're not particularly good probability distribution. So we'll get into that a bit more later. Yeah.
I think you kind of answered. I was wondering if the iterative nature of training was kind of pushes it to actually become.
I think it's the optimal answer that training would give you if training went perfectly. And if training went perfectly, it will match the actual generative distribution of the text that you're trying to model. Great. So how do we optimize these parameters? We do that through gradient descent. And the way we do this is we calculate the gradient of the loss function with respect to the parameters. How do we do this? In general, we use the chain rule of probability, or the chain rule of, derivatives. And we calculate the, we basically use backpropagation, which is a method to kind of do dynamic programming to calculate the probability of the parameters, or the probability of the loss given the parameters. We're going to talk about this in more detail in later classes. So this is the mathematical definition. The last mathematical definition is you pip install torch and it will do it for you. And so like in reality, that is what we do a lot of the time, because there are good libraries that can do this for like arbitrarily complex functions. I will go into the details because we need to do that for the class. And then after we do this, we update to move in a direction that decreases the loss. So as we said, the loss is something that we want to decrease if the model is doing, we want to be low if the model is doing well. So we multiply this by a learning rate, alpha, and we move in the direction that would decrease the loss. Notably, this is something called first order gradient descent. So it's calculating the probability of each parameter independently and moving in that appropriate direction. There's also more complicated methods that can optimize things more efficiently, such as Newton's method, LBFGS. They consider the curvature information and converge more quickly, but they also use a lot more memory. And also they're not used super widely in neural networks because they can also sometimes overfit and fall in local optima more easily than first order methods. So one thing that you should know is these are very good things to be using if you're optimizing a small number of parameters that have a very large effect on the model. So if you are optimizing only like 5 parameters or 8 parameters and each one is super important, then you might want to consider these second order methods. Okay, great. Any questions? We'll go into more detail, of course. Okay. So I'd also like to talk a little bit about evaluation. Evaluation is very, very important. And to do model comparison, basically we've built 2 models. Like let's say we built a generative model and a discriminative model. How do we tell which one is better? And what we do is we train both on the same training set, evaluate on a dev set, and compare scores. And maybe if we've done a lot of experimentation, we feel we're basically done with hyperparameter tuning, we'll evaluate them on the test set. For text classification, evaluation is relatively straightforward. We have accuracy. So what percentage of the labels do we get correct? Another really important concept if we're evaluating accuracy is the chance rate. And the chance rate is basically, what if we did the like silliest possible thing we could do? Like say every single sentiment is positive. What is the score that we would get? And the reason why this is important is because accuracy can be deceptive. Like, for instance, we might train a spam classifier or like a, we might train a spam classifier or a toxic language classifier and get 99% accuracy. And we might feel very happy for ourselves. But then when we realize that spam is only 1% of the posts, or toxic language is only 1% of the posts, we realize that we could do the exact same thing with like something that says it's never spam or it's never toxic language, and that's not very useful, right? So if you're using accuracy, you should always calculate the chance rate. Remember to do that. So instead of this, especially when we have a particular class that we really care about, like we care about the spam class or we care about the toxic language class, we can calculate precision or recall or F1. So precision is the percentage of system outputs that are correct. So like, this might be the number of times the system output the spam label. And this would be the number of times the system output the spam label and it actually was spam. Recall is the number of actual positive classes that you get correct. And then F measure is the harmonic mean of both. So you do 2 times precision times recall divided by precision plus recall. And F measure or F1 score basically penalizes when you have really bad precision or really bad recall. So you kind of need to find a good balance of both. So this is a really, really important concept that I want more people in NLP to be careful about. And because I want more people in NLP to be careful about this, this is required for your second assignment. So there's no way around it. There's a way around it, but you'll get a worse grade, so I wouldn't suggest it. And it's statistical testing. And the basic idea behind statistical testing is that we have two models with similar accuracies. Like, let's say we have a generative model that does 85.4 on data set 1, discriminative model does 85.3, 91.5 and 90.2, and then 56.7 and 57.0. How can we tell whether the differences are due to like actual consistent trends that hold across the data sets, or are they just by chance? And if we had a slightly different data set that was still nonetheless very similar, we would have a similar result. Yeah.
The higher thing like that is like, you really want 3 digits.
Another hard thing is, do you really want 3 digits of accuracy here? Or maybe we want 2, or maybe we want 10, who knows, if we're doing physics, we probably want 10. So the answer to this is statistical significant testing. I'm going to cover it briefly here, but there's a very good reference that I've cited here, The Hitchhiker's Guide to Statistical Significance Testing in Natural Language Processing, where you can read more. And the important thing about statistical significance testing, the basic idea is, given a quantity, we want to test certain values of certainty or uncertainty with respect to that quantity. And we have a p-value, which basically tells us what is the probability that a difference with another quantity is by chance. And the p-value being lower is that there's more likelihood of a significant difference. And another thing we can do is we can calculate confidence intervals. And the confidence intervals tell us what is the range under which we could expect another trial to fall, sorry. So if we did another trial, what is a likely value we would have gotten from that? Yeah.
I was wondering, I haven't seen these very often in NLP, but how common are corrections like Bonferroni correction?
How common are corrections like Bonferroni correction? Can I return to that question later? I'll talk about unpaired versus paired tests. So an unpaired test compares the means of a quantity on 2 unrelated groups. An example could be a test of a significance of a difference of accuracies on a model between 2 data sets. And what I mean by this is, like, let's say we have model A, let's say we have our generative model, and we want to answer the question, we have data set 1, we have data set 2. How likely is it the case that data set 1 is essentially harder for this generative model than data set 2 is? And these 2 data sets are completely different data sets. They have different data, they have different numbers of data points. And because of that, essentially there's no way to find like a correspondence between the data points or anything like that. There's also paired tests, and these compare the means of a quantity on 1 data set under 2 conditions. And an example of this, I'll get to it in a second. An example of this could be testing the significance of a difference of the accuracy of 2 models on 1 data set. So here we have our generative model, our discriminative model, and we want to calculate whether the difference between the 2 is something that's like actually real or just by chance based on data selection. Yeah.
The accuracy itself, like the aggregate statistic on the whole list, this accuracy is plural or
well, we have 2 data sets, so we have 2 aggregate statistics, right?
would it need like a sort of sample of accuracies to do a t-test or something?
So each data set has multiple examples in the data set. And one way you can think about it is like I'm mainly for the tests, I'm mainly talking about tests specifically with respect to data set selection. So like you, yeah, actually, this is a good point that I should have clarified more. So thank you for asking the question. So the question is, don't you need an aggregate like statistic in order to calculate a significance test? And if you've taken a statistics course, then you'll be familiar with this. And the idea is we have like two groups. We calculate an aggregate statistic over the groups, and then based on that, we want to know whether the aggregate statistic that we calculated on the groups is kind of like significantly different. If we selected another group according to the same data generating distribution, would we get a different, significantly different result or a similar result? Here, the groups that we're talking about when we talk about a data set are the examples within the data set. So each example in the data set we assume it was drawn independent and identically distributed from a particular data generating distribution. And so because of that, it's an aggregate statistic over all of the examples.
Yeah. How does this sample have an accuracy? You can be 90% accurate.
So it's each individual sample has an accuracy of 0 or 1, basically. And then the average of them is the average. Yeah, sorry, these are good questions that I should have a better answer for. So I'll try to fix the slides next time, and we can clarify on the outside if there's any issues. So this is really important. The idea of paired versus unpaired tests is really important. And one important thing to know is if it's at all possible to do a paired test, the paired test will be more likely to accurately identify statistical differences. So if you use an unpaired test when you have paired data, you're basically much less likely to get a significant difference. And the reason why this is the case is, let's say we have one, let's say we have one system that gets an accuracy like this. We get one system that gets an accuracy like this. And then we say, well, what if we resampled our data set and got some subset, or no, okay. Sorry, I'll get back to this after I explain the Bootstrap test because it'll be easier to explain then. Okay, so Bootstrap tests, basically what these are a very convenient way of calculating statistical significance because they're basically universally applicable. They have some downsides too, but they're universally applicable. So you know that you'll always be able to at least run a Bootstrap test and get an answer for it. And the way it works is basically you resample the data set and you calculate whatever thing you want to calculate, like accuracy based on this resampled data set. So what you do is you sample many, for example, 10,000 subsets from your dev test set with replacement, and you measure accuracies on these many subsets. And a very practical implementation is like if you're familiar with NumPy, you can use the np.random.choice function with replace equals true, and it will basically subsample data from your data set. You can do this, and then you go in and you calculate the accuracy on this subsampled data set. And so what you do is if you want to calculate a confidence interval, you can resample the data set 10,000 times, and then you sort the accuracies, and you get the 2.5% from the bottom, 2.5% from the top, and anything that falls within that interval is within your basically like 95% confidence interval. So you throw away the like outlier ones, and you keep only the ones in the middle, and these are the ones that kind of are most representative of the range of potential accuracies you could get from the data set. Another thing that you can do is you can sample a data set once and then calculate the accuracy of two different systems over the same data set. And this is how you do a paired test. So you subsample a data set, you calculate the accuracy of model 1 and model 2, and then you see which one wins more often. So if model 2 wins in 98% of those data sets, basically your p-value is 2%, because your model has won 98% of the time out of all the trials you did. And typically like 5% is treated as like a significant difference. It's kind of arbitrary, but it's like standard experimental practice. And because of that, like if you got 98% wins, then you can say you have a significant difference. The nice thing about this is very easy to implement, applicable to any evaluation metric in bias, but it has two downsides. One is that it's somewhat biased on small data sets. So if you have very small data sets, it can either be either too aggressive or not aggressive enough, depending on like the characteristics of your data set. So it might like overestimate or underestimate whether there's an actual significant difference. Another problem is that it's very slow, because you need to sample more samples to get an accurate result, and sampling those samples and calculating accuracy can be slow. So I got a question about explaining the Bootstrap test once again, and there was a question about the implementation logic, but I could actually show an example, which might be even easier. So hang on 1 second while I pull it up. And it's actually in, I believe it is in this this notebook, which is the notebook for this class in the ANLP code repository. And here at the bottom, we have the eval with paired bootstrap function. And basically, this is implementing a paired bootstrap test. And so here we have our inputs, which are gold, the correct labels, system 1 output, system 2 output. We have the number of samples, and also the ratio of samples to take every time. And what we do is we calculate scores for each of the systems, and we calculate the number of wins. And the way we do this is we iterate the number of samples. We do a choice of the samples like I talked about before. So we sample with replacement the IDs of all of the samples we're going to be using. And then we take a subsample of each of these, and we calculate the accuracy for both. And then if system 1 is better than the other, then we say system 1, 1. If system 2 is better than the other, we say system 2, 1. And then if both of them have the same score, we say they tied. And then down here, what we do is we basically print out like what percentage of the time this is correct. So I encourage you to look at this code if you'd like, or reuse this code for when you're evaluating your assignments. Cool. So when we resample, I got a question on Zoom. When we resample, how much smaller is the data set? If you're sampling with replacement, you can actually sample the same size, but you can also sample 0.5 or something else. If you make the number of samples that you take smaller, then it's basically simulating the case that you had a data set of that size. So taking the same number is pretty reasonable, or taking half is pretty reasonable as well. Okay, yes. That was a paired test. There's actually code in there to do the confidence intervals as well, because it's aggregating all the scores, and then you can go in and sort them. So you can see both in that example. Yes.
What is the significance of context?
What? Sorry, I couldn't hear.
What is the significance of a non-test?
What is the significance of a non-paired test? Or how do you measure significance with a non-paired test? So a non-paired test, I can go back and show this example. So if you want to compare these two things, you can do a paired test because this is from the same data set. And the examples that you're testing your generative and discriminative classifier on are the same. So you can basically like resample the same data set and compare the scores from the same data set to each other. However, if you have data set 1 and data set 2, and you want to tell if the difference between data set 1 and data set 2 is significant, then you wouldn't be able to use a paired test because the examples in data set 1 and data set 2 are different, basically. Like data set 1 might have 100 examples, and data set 2 might have 1,000 examples, and there's no way to make a correspondence between them. So there are some cases where you can't use a paired test and you only can use an unpaired test. Another example is if you wanted to know the difference in height between people from two different countries, like let's say we wanted to say, are people from Canada or people from the US taller? If we did something like that, there's no way to pair, like you can't come up with an arbitrary match of me to a random Canadian person. So because of that, you'd have to use an unpaired test. Any other questions? Okay. Yeah.
Paired test and the bootstrap test is finding the p-value part from the paired and unpaired test. The bootstrap test is accumulating the average.
So the bootstrap test can be used in a paired fashion or an unpaired fashion. So like a way that you could use it in an unpaired fashion would be, I actually almost never do this because there's very few situations where you actually need to do this. But essentially, if you did an unpaired test, I think what you would be doing is you would be subsampling data sets, but you'd be doing it independently of each other. And then you could just compare maybe the number of wins between the independently subsampled things. So in the code that I showed, you subsampled the data once, and then you calculate the accuracy of both models on it. But imagine if you subsampled the data without using the same data set for each one and then compared the wins, then that would be unpaired. And the reason I can show you now the example that I had here, the reason why paired tests are intuitively better. Let's say these are accuracies on, let's say these are accuracies on like 5 data points or, scores on 5 data points. If you did a paired test here, every single time system 2 is better than system 1. On every single example, system 2 is better than system 1. So no matter which way you subsample data from here, the score of system 2 would always be better than system 1 as long as you subsampled the same data points. However, if you didn't worry about subsampling the same data points, you might get a sample from down here and then from up here. And if you did that, then system 1 would look better than system 2, right? Because you happen to get examples. You happen to get easy examples when you sampled for system 1 and hard examples when you sampled for system 2. So that's the power in like hard examples tend to be hard for all systems. Easy examples tend to be easy for all systems. So because of that, that's how pairing kind of like removes the variance of the difficulty of the data set and only looks at the like relative advantage of all systems.
Why are we calculating the wins? You can get the accuracies for both data sets in the test with them. Why get the wins for both?
So very, very good question. So you can calculate, the question was, why are we calculating the wins and why don't we calculate the, let me see if I can rephrase it slightly. You can calculate the accuracies for each example and take the difference between them. Is that what you mean? Like plus.
How far they're 0?
Yeah, and so basically, like one thing that you could do is for each example, you calculate the difference in the accuracies between the examples, and then you do a t-test or something to see if that is different from 0. That is great for things where the score is the sum of the scores of all of the examples, but that's actually not the case for many evaluation metrics in NLP. One example being F measure. The F measure is not just the addition of all of the component scores. It's there's the complicated harmonic mean that goes into it, and because of that, there's no way to calculate F measure using a t-test. So you need to use something like a Bootstrap. Okay, great. So at the very end, we're approaching the end of the class. I just want to go very quickly through some text classification data sets. There's so many out there that, like it seems like almost a futile exercise to go through this, but just to introduce a few. There's the Stanford sentiment tree bank, which was the example that we were using before. This is basically a very famous tree bank. It's used in addition to standard tags. Each has a syntactic phrase tagged with sentiment. So that might be a little bit hard to see on the screen, but basically it has the syntactic parse in the sentiment of all subphrases, which is kind of interesting. When we're looking at data sets, it's also really important to think about like what data was it collected on? What was the original data it was curated from? And why did we curate the data set? So it was created from reviews from RottenTomatoes.com, collected in 2004. This might be kind of useful information to you if you want to train a sentiment classifier and want it to be good on things from like 2022, for example, because all of the actors who were born in the past, 30 years are probably not going to be in this data set. So, maybe that's a good thing to know. The annotators for this were people from MTurk, so they got MTurkers to read the outputs, and they actually didn't mention in the paper how they filtered out the people from MTurk and found good people, as far as I remember. Another very popular one is AG News. Its news articles categorized into 4 classes. The data is from an academic search engine, also coincidentally in 2004, coincidentally or not coincidentally. It might have been the golden age of machine learning-based text classification. And it was created as a test bed for data mining in IR, but now it's used kind of to evaluate text classification models as well. There's also the Dbpedia Data Set, which is pretty widely used as well. It's classification of Wikipedia entity description text into 970 or 219 classes. Data is from Wikipedia first sections. And the curation rationale is as a test bed for text categorization. One interesting thing, I created these slides last year, and one interesting thing I found was actually for text classification data sets, surprisingly few of them were, or most of them were created to test ML models. They weren't created to actually solve any problem that anybody was having, which was kind of surprising to me because there are plenty of problems you can solve with text classification. But I just found that the most popular data sets were created just as test beds. So that's maybe potentially interesting for you. Great. Okay, so that's what I have for today. Are there any questions about the overall content or? Oh, chat question. For the Wikipedia table, was representing tables ever attempted? Are you talking about this here? There is work on representing Wikipedia tables. Yeah, this is text, and there is work on representing tables, but that's maybe another class. Yeah. Okay. Thank you, everybody, and I'm happy to answer any individual questions up here as well.